All right. Uh, Today we're going to look at section 6.4, sampling distributions. And this is going to be kind of a real short section. It's just kind of reviewing some topics and getting us ready to see where we're going to go in future sections. So just a quick review here of some different terminology we're looking at. Population. Just a reminder what that is. That's the entire group um, that we are interested in studying. And really, that can be anything. You know, it could be like the entire population of the United States. That could be the population we're looking at of people. It could be the entire number of let's say dogs that are kept in a humane society, a local humane society for an entire year. That could be the population we're studying. It could be, I don't know, all customers who go through a store on a given day, on that particular day. That could be the population you're looking at. So it's just whatever group, the entire group, and that's the big thing. It's the entire group that you're looking at when you're talking about population. Now, a sample is a portion of a population, um, that is studied to estimate information about the population. And this should be random. And in earlier sections of the book, they talked about, how some things you can do to try to make a random sample there. But the big thing is this is a portion of the whole population. So, like, let's say I was looking at the dogs at a humane society for an entire year. So instead of looking at uh, each dog every day of that, maybe we have like certain set days, like the first of every month we check, see what's going on, how long has the dog been there, are they healthy, or whatever we're interested in about that. And we'll measure, or maybe it's just how many dogs we have in there. So first of every month we go, okay, how many dogs do we have in there? So we're not taking every day, we're just sampling, we're taking samples, and then we're going to use that to estimate for the entire year. A parameter, this is a numeric measure of the population. And on the next slide, we'll talk about some examples of parameters, but parameters refer to things about the whole population, some numeric number about the population. So the most obvious one would be some mean value of the whole population. So like if I'm doing that dogs in the humane society type of situation, what's the average number of dogs they have on any given day during there. So there is some true average, but you could, and that would be the population parameter. But if we just sampled, and figured out that average, that would be the statistic. So the statistic is a numeric measure of a sample, and this should be representative of the whole population. So it should be representative of a parameter. So, maybe for some reason we can't measure how many dogs or whatever are in our humane society thing there. So every day, this would just say, well, okay, this is going to give us an estimate for what that average number of dogs we keep on a daily basis is. So that would be a sample statistic. So statistic goes with sample. Parameter goes with population. It's a, it matches up perfectly. Alliteration, I think is what they call it, right? So, all right. So here are some common statistics and parameters that we would see. So mean, for a statistic, we say X bar, and that's how you say it, X bar. And then for parameter, we use mu, the Greek letter mu. So that's mean, or what most people would think of as average, but we don't want to use that because in statistics, average could mean mode or median as well. So we're specifically talking about mean. Then the next one, variance. And so when we use a sample statistic, for variance, it's S squared. And then for the population, it's sigma squared. So Greek letter sigma. And then standard deviation, remember, that's the square root of the variance. So that's just S or just sigma. And then proportion. Now we've talked about proportion before, and we use P, and Q was like the when you talked about binomial experiments and what's the probability of success, probability of failure. So we use P for the probability of success. We use Q a lot of times for the probability of failure, or 1 minus P, the complement of it. But here's a new one that we haven't done before, and that is P hat, the little P with a little mark above it. And that is a statistical proportion measurement. So you do a statistic, a sample, and you say, oh, okay, what's the proportion in that sample? That's P hat, and it's supposed to be indicative of the actual population proportions. So that's something new we haven't seen before, but there's a few different things we've seen, and their names. So what I would like you to do is go ahead in the textbook, do problems 1 through 4, all of them, and then start the video up again, and we'll continue on. Okay, so I assume you're done with those 4, and let's move on to the next part. So types of inference. So inference, what inference is using a sample and its statistics to tell something about the population, right? So that process of looking at the samples, looking at the statistics you calculated from those samples, and then saying, okay, this is indicative of somehow of the population. That whole process is called inference. So when it talks about inference, that's what they're talking about. Now, there are some different ways of doing inference. You could just, do an estimate. So you could estimate the value. And then, a lot of times people think that just means like you make a guess, right? And that's not true. You can base it on samples you've looked at. And that's probably the most common thing we're going to look at is estimating. The big thing here is you collect the data that's already there, and you use it to make an estimate of a population parameter. Okay, as opposed to testing. So testing, instead of just taking the data that's already there and looking at it, sampling some data that's already there, this is actually, you're going to set up experiments. You're going to formulate a decision about the value of the population parameter. You're not just going to take the data, you're going to go out there and say, okay, let's figure out a way that we could get a good read on that. But again, you have to make sure when you're doing this, when you're doing samples, the samples are random. That is critical. You can't say, well, we're going to talk to this group of people, or we're going to go to this thing. It needs to be random. It needs to have some kind of random number. Regression. This is when we predictions or forecasts about the value of a statistical variable. So when we're doing regressions, we're looking at what has already happened and then using that to predict what's going to happen in the future. What if I've done this study and I've done that study, and I've had, like, let's say, a certain standard deviation, and I go, okay, it looks like the standard deviation works this way. I'm going to do a sample in the future and I'm going to make a prediction. It's going to be close to this number. That type of thing is regression. Now, one of the ways we're going to do that is we're going to look at later on taking a bunch of data and making a line or something to do a regression line, but we're not doing that right now. So, but these are different ways. You can do estimates, you can test, or you can do regressions. All of these are ways of trying to infer something from a sample about the population. Okay, so let me have you answer question number 5. We'll pause the video and then we'll go on. Okay, so let's go to the last one. This is probably the most critical thing we're going to look at in this section: sampling distributions. So this is a sampling distribution is a probability distribution of a sample statistic based on all possible simple random samples. Again, it has to be random. Of a set size from the same population. Okay, so what is all of that talking about? What is that all talking about? Okay, so let me kind of give you an example here. So we have some kind of population distribution of something. Okay, a lot of the population is centered in the middle, and then as we move away from there, you get fewer and fewer members of the population. Think about this as like how many people said this. This is a measure of how many. Think of these like bar charts or histograms. How many people said that? How many people said this? How many people are this tall? How many people are this tall? So on. So most of the people are going to be in the middle, and then you kind of go off from there on both sides. Now, what happens when I take a sample is I don't get something that looks just like that. I might get a person that's in this area, and I might get a person that's over here, and I might get a person that's over here, and I might get a person that's over here. And so the question is, when I get that sample, when I take that sample and I calculate the mean, right? This has a mean. This is mu. That's its mean, the population mean, right? But when I do my sample, like let's say I did a random sample, and I just, how it worked out is I got a person here, a person here, a person here, and a person there, and a person there, and a person there. Well, if I calculate the mean of those values that I would get from there, it would not be on mu. Look at it. There's more data on the right-hand side than is on the left. So if I were to say, okay, well, where's my mean? If this is like, let's say 150, here's 150, my actual sample mean might be over here at like 162 or something. I'm just making up numbers here, but it would be off. It would be off center. Okay. So what if I take another sample of that size? Well, I'm not going to get the exact same numbers. I'm going to get different numbers. This time I might get somebody here and here, and maybe somebody around there again, somebody around here, and somebody around there. So this time, I get these numbers, and these should be the same size. I should have counted 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, and then maybe there's somebody here, 6, and maybe there's another person here, 7. Okay, so they should all be the same size. So I'm going to call this the mean I got for the first one. And then I do the mean of the second one. And I get it again. If you look at my little square boxes here, it looks like there's more on the left-hand side this time. And so my second mean, maybe it's over here at 147 or something. If I keep taking samples like that, what's going to happen is I'm going to get, more and more values, more and more mean values. Maybe I get another one that's like right around that one, but I'm going to get more and more mean values. And it's going to be, sometimes I'll get like a really strange sample where it's all this group, oh, okay, that could happen. My mean would then be way over here on the edge, but what's going to happen is I'm going to end up with, a bunch of samples here, and it's going to be grouped around my actual mu. This spread of the averages, the average calculation, that's the sampling distribution. That's what this is talking about. It's not the whole population. Instead, it's just, I calculate an average. I calculate another average. I calculate another average. If I could calculate every single group of every single average, what I would find is it would create a normal distribution right around the actual mean. Sometimes above it, sometimes below it, but I'm always like kind of close to it, because most of the time I take a sample, I'm going to get somebody that's in that middle area most of the time, because that's where most of the people are, or most of whatever population I'm looking at are going to be at. They're going to be in the middle area. So I'm going to, over time, build up this mound right around the mean, the actual mean. So that's the sampling distribution. And we're going to talk about this sampling idea more in the future. But that's the idea, is that what we're doing is we're calculating, you got sample 1 and it's got a mean. I shouldn't use S. Sorry. I don't want you to say standard deviation. I'll say group 1. Let's do that. Group 1, and it has a mean. And then I have group 2, and it has a mean. And I do group 3, and it's got a mean. And if I were to take all these values, it would create this distribution. So that's what it's talking about. That's what it's talking about. Now, what you'll notice is this will have a smaller standard deviation than the original population. It'll have that. So that's something we'll talk about also. All right. So let's finish up this section. Go ahead and do 6 through 9 all. And that's all for this section. So I will talk to you later.